Hello, Advanced Physics MT3 C part. So, question number 10. Using uh, Einstein formula, E is equal to mc square of if m is the mass in gram and c is in usual 3.0 into 10 power 8 meter per second. What is the unit of energy in this setting? It is something error. Option A, millijoule, B, joule, and C, kilojoule. So E is equal to mc square. So this is it should be in kilogram, but it is, so this is kilogram and this is meter square. Multiply by both sides into this one, 10 power minus 3, 10 power minus 3, 10 power minus 3. This one is now in grams. So this is in millijoule. So answer is A, millijoule. Question number 11. Storing electrical energy in a capacitor, show that the work done to charge a parallel plate capacitor. Parallel plate capacitor is W. W is equal to P A V square over 2D. P is electrical permittivity, A is the area of the plate, V is the voltage, and D is the thickness or separation of dielectrics. When Q, we will use these two equations. Q is equal to CV, this is equation number 1, and C is equal to P area into divided by thickness. So this one. So work done to charge a parallel plate capacitor is W. So the W is equal to Q square over 2C. Using, this is the third equation, this is the three equation, we will use this one. And now using equation 1, so Q, so we place this one, so Q square V square over 2C. So we have a expression which is equal to half CV square. So this is now using equation number 2. So C 1 over 2, C is P area over thickness into V square. This is equation number 4, which is the required equation. So this is equal to P A V square over 2D. Question number 11. It's a B part, safe continued. Also, if the capacitor is limited by the breakdown voltage of its dielectric, which is proportional to the thickness, so V maximum is equal to B into D. B depend upon the material and D depend upon the thickness, is the thickness. The question is how the maximum energy stored in a capacitor depend upon the mass of the dielectric, its density D, and other constants. So V maximum is equal to BD. B is the breakdown, uh, depend upon the breakdown, depend upon the material, and D is the thickness. So W, the work done, is equal to the energy. Energy we have just calculated is a P area into V square over 2D. So V is a maximum, so we will substitute this value, this one. So this is equal to P area B square over into D divided by 2. So the volume is AD. A is area and D is the thickness. So this is equal to V volume. So remember, this is V volume and this is voltage. So voltage, we will use another term. So it is equal to, if you substitute this one, so this and this is equal to volume. So rho P B square into volume divided by 2. This is the work done. So now the mass of this one is equal to density multiplied by volume. Density is D, so volume is equal to M over D. So mass of the material used in the capacitor is M over D. So if we substitute this one, E maximum is equal to P B square over 2 into volume, and use this new term. So volume is equal to this one. So this will be equal to M P B square over 2D. So that is this one is depend upon the B and D. If P is given, which is the 2 and 10 per minus 11 uh, Faraday meters per meter, B is given 2 into 10 power 7 volt per meter, D is given 1000 kilogram per meter, just water. So M is equal to 1 kg. So E, the maximum energy, breakdown energy, is if you substitute all the values in this one. So this is equal to 4 joule. Comment on the practicality of using the capacitor of this type. So output from 1 kilowatt uh, output from 1 kilowatt wind turbine. Wind turbine is 1 kilowatt, which is 1000 joule per second, but the capacitor is 4 joule, is too low and is not viable. So compared to wind turbine, which has 1 kilowatt energy work done, so 1000 joule per second. So for compared to this one, this capacitor, this storage is 1 joule, which is very low, so it's not viable. So that's the end of the C part.